This is the screencast for section 7.2, example 1, areas in the plane. So we've been finding an area under a curve and between the x-axis this whole time. Now we're going to find the area between two curves. Now this is another one of those things where in calculus you've actually been doing this the whole time, you just didn't know it. You've been finding the area in between a curve and a horizontal line on the x-axis, so y equals 0. So that really y equals 0 didn't affect your equation at all. Now the curve is going to change. So the area between two curves is defined by the book as where f of x is greater than or equal to g of x. It's going to be the antiderivative from a to b of f of x minus g of x. So basically it's always going to be the top minus the bottom function. And you'll see that in these three situations down here. So first of all, if you take all the area under f of x and then you subtract out, so that's the top curve, and then subtract the area under g of x, you get the full area between f and g. Now what if one of them is above and one of them is below the x-axis? Well, if you take the area under f of x and you subtract the area under g of x, remember the area under g of x is negative, so you're really adding those two areas together, which then would create the two pieces that would make up the area between f and g. Now if both of them are below the x-axis, you're taking the area under f of x and subtracting out the area under g of x. So this is going to be an overlap of f of x would be positive, but g of x would be negative there because you're subtracting a negative area. So what's remaining then is the area between f and g. And as you can see here, the area between these curves is always the same, and your setup for integration is always the same. Your work might be a little bit different. In example 1, it says find the area of the region between y equals secant squared of x and y equals sine of x from x equals 0 to pi over 4. Well, that's my upper limit or lower limit and upper limit of integration, but I'm going to integrate from 0 to pi over 4 then of the top function secant squared of x minus the bottom function sine of x. So I'm getting this full area minus the area below sine of x, which leaves me with the area between the two curves. And I could do this by hand. Integral of secant squared of x is tangent of x. Integral of negative sine of x would be positive cosine of x. I'm evaluating from 0 to pi over 4, so I'll plug in pi over 4, subtract plugging in 0, simplify, and I get square root 2 over 2. Then I'll try problem number 1. Find the area of the shaded region analytically. So we're finding the area of the region between y equals 1 and y equals cosine squared of x. Well, it doesn't give you a lower bound and an upper bound of integration, so I'm going to have to figure those out at this time, but I can see that it's 0 and pi. So I'm going to integrate from 0 to pi of the higher function 1 minus the lower function cosine squared, and that'll give me the area in between the two. But it's the antiderivative of sine squared of x, which I don't really know, but if I use a property, a trig substitution, I can say that sine squared is really 1 minus the cosine of 2x all over 2. So I can put that 1/2 on the outside and integrate that pretty easily. Antiderivative of 1 is x. The antiderivative of cosine is sine, so still of 2x, but now I'm going to divide by du, divide by the 2x, so 1 over 2. And of course you could use u substitution there if you need to, but that's a pretty straightforward one. Now a little fundamental theorem part 2, and I get pi over 2 units, and I checked that in my calculator just to make sure.